Hello everyone, I am Dr. Samyukta S, Assistant Professor, Department of ECE at SJBIT. In this video, I am going to explain you about the counters, that is, what is counter, what are the types of counter, and what are the applications of counters. Okay, see, a counter is a sequential digital circuit that counts the number of clock pulses applied to its input. It changes its output state according to a predetermined sequence. Counters are built using the flip-flops and are widely used in digital electronics for counting events, generating timing signals, and frequency division. So it is made up of using the flip-flops. It operates using the clock pulses and it stores the count in binary form. And it is essential building block in digital system. Okay, so counters are used in digital clocks, timers, frequency counters, traffic light counters, elevators, etc. So coming to the definition, a counter is a sequential logic circuit that progresses through a prescribed sequence of states in responses to clock pulses. Each incoming clock pulses increases or decreases the binary count here. Okay, so the counter requires a flip-flop. Here the output depends on both the present input and the previous state, and it can count upwards, downwards, and both. Okay, so binary counter. A binary counter counts in binary number. Here each flip-flop represents one binary digits, that is bits. For n flip-flops, the maximum number of states is 2 power n here. Suppose if there are two flip-flops, it requires 4 states. If it is 3 flip-flops, 8 states. If there are 4 flip-flops, 2 power 4 is 16 states. So there will be a 16 states. Okay. So here I have considered a 2-bit data. So we will get a 4 possible combination here. So if the present state is 0 0, the next state will be 0 1. If the present state is 0 1, the next state will be 1 0. If the present state is 1 0, the next state will be 1 1. If it is 1 1, the next state will be 0 0. It will going to work in a loop. Okay. And n-bit binary counter consists of n flip-flops and can count in binary from 0 to 2 power n minus 1 here. Okay, so as an example of binary counter, here have represent each and every state in this table here. This is the state table. So here you can observe here that the present states are represented by Q0 and Q1. Input is represented by X and the next state is represented by Q0 and Q1 here. Okay, so if the present states are 0 0 and if the input is 0, the next state will be 0 1. If the present state is 0 0 and if the next input is 1, the next state will be 1 1. Similarly, if the present state is 1 1 and if the input is 0, the output will be 0 0. If the present state is 1 1 and if the input is 1, the next state will be 1 0. Here the least significant bit, that is Q0, changes for every clock pulses here. Okay, but the Qn changes for every 2 clock pulses. Suppose if there were Q2, Q2 will be changed for every 4 clock pulses. Fine. This property allows counters to divide the input clock frequency. Coming to the applications, see, counters are used extensively in digital systems. The very best example is digital clock. The counters are used to count seconds, minutes, and hours in the digital clock. Counters are also used as a frequency divider. There, each flip-flop divides the clock frequency by 2. The counters are also used in traffic light controllers. There the counter controls the duration of red, yellow and green light. It is also used in event counters to count external events such as sensor signals, etc. Next, let us see which are the categories of the counters. So there are two main categories in the counters. So that is, counters are classified into two main categories. One is asynchronous counter and another one is synchronous counter. Asynchronous counter is also called as a ripple counter. Here in the asynchronous counter, flip-flops are not driven by the same clock. Only the first flip-flop receives the external clock and the remaining flip-flops are triggered by the previous flip-flop. It is very simpler in design and it is slower due to propagation delay. Coming to the synchronous counter, here all flip-flops receives the same clock pulses. Here the output changes simultaneously. It is comparatively faster in operation and it is preferred in high-speed applications. So now let us discuss about this in detail. So the first category is the synchronous counter. And synchronous counter is also called as a ripple counter here. Only the first flip-flop receives the external clock. The output of one flip-flop acts as the clock input for the next flip-flop. Okay, so the advantage of this asynchronous counter is it is simpler in design, requires very few logic gates, easy to implement. Coming to the disadvantages, it is having a propagation delay, slower for large counters and not suitable for high-speed circuits. So here as an example, I have considered the T flip-flop here. So this counter is called asynchronous because not all flip-flops are having the same clock. So look at the waveform of the output here. Here in the timing diagram, it resembles a clock as well. This provides a clock that runs twice as slow. If we feed the clock into T flip-flop where T is hardwired to 1, the output will be clock whose period is twice as long here, as you can see in this timing diagram. So here I also consider a JK flip-flop as an example here. So 2-bit synchronous counter uses 2 JK flip-flops here. Okay, so as you can observe here that the clock input is given to only the first JK flip-flop. Okay, so here the external clock is connected to the clock input of the first flip-flop only. So it changes the state at the negative edge of each clock pulses here, but the next flip-flop changes only when triggered by the negative edge of the Q output of the first one. You can observe that in this waveform here. As you can see here, after every clock pulses, Q0 toggles every pulse. See, Q0 will going to toggle at every pulse, but Q1 will going to toggle only when Q0 changes from 1 to 0. So here, depending on the flip-flop triggering, here the Q1 toggles only when the Q0 changes from 1 to 0 here. Okay, so if clock frequency is F and Q0 frequency is equal to F by 2, then Q1 frequency will be F by 4 here. Hence, counters are used as frequency dividers. Okay, so you can observe the propagation delay. So this propagation delay exists because the second flip-flop always waits for the first flip-flop. Okay, so this is how the counter will going to work. Thank you.